Today's topic is resistors and counters. A resistor is a group of memory elements which can store a binary word and can modify the stored word by shifting its bits left or right or by performing other operations. So, resistors are devices which can store binary words, and this word can be modified. A counter is a special kind of register designed to count the number of clock pulses arriving at its input. First, we consider about the registers, devices that can store binary words and can modify them. Simplest kind of register is a buffer register. A buffer register is the simplest kind of register which can store a digital word. Figure A shows a buffer register built with positive edge triggered D flip-flops. So this is the simplest kind of register, that is buffer register. It is shown in this figure. Here 4 positive edge triggered D flip-flops are used. These are 4 D flip-flops with positive edge triggering. This is the clock pulse which goes to each of these D flip-flops. This is one D flip-flop. Input data bit D0 is X0 and its output bit is Q0. This is the second D flip-flop. Its input data bit D1 is X1 and its output bit is Q1. This is the third D flip-flop. Input data bit D2 is X2 and output data bit is Q2. And this is the fourth D flip-flop. Input data bit D3 is X3 and output data bit is Q3. This buffer register can store a binary word Q3, Q2, Q1, Q0. These 4 bits are obtained from outputs of these 4 D flip-flops. Figure A shows a buffer register built with positive edge triggered D flip-flops. The X bits set up the flip-flops for loading. These are the 4 X bits: X3, X2, X1, X0. X0 goes to D0, X1 goes to D1, X2 goes to D2, X3 goes to D3. These are the input bits of these 4 D flip-flops. So these 4 X bits will set up the flip-flops for loading. Therefore, when first positive clock edge arrives, the stored word becomes Q3, Q2, Q1, Q3, Q2, Q1, and Q0, it is Q0. Correct this. Stored word is Q3, Q2, Q1, Q0. And when positive clock edge arrives, this stored word becomes X3, X2, X1, X0, because D3 is X3, and as soon as the positive clock edge arrives, this Q3 becomes D3, that is X3. So Q3 becomes X3. Similarly, Q2 becomes X2, Q1 becomes X1, and Q0 becomes X0. And the stored word Q3, Q2, Q1, Q0 will be X3, X2, X1, X0, or Q equal to X. Next is controlled buffer register. In controlled buffer circuit, we also use these 4 D flip-flops, positive edge triggered D flip-flops. There are 4 positive edge triggered D flip-flops. This clock signal goes to each of the 4 D flip-flops. This additional CLR signal also goes to all these 4 D flip-flops. Work of this CLR signal. CLR is for clear. Work for this CLR signal is to clear the word by means of clear. Clear means we have the word 0, 0, 0, 0. This figure B, shows a controlled buffer register with an active high CLR. Active high CLR means when CLR is high, it will be active. And it is active, it means the output word is now clear, that is 0. So output word will be 0, 0, 0, 0 when CLR goes to high, because it is active high CLR. When CLR goes to high, it will be active. It means the output is now clear, that is 0, 0, 0, 0. When CLR goes high, all flip-flops reset and the store word becomes Q equal to 0, 0, 0, 0. Q means Q3, Q2, Q1, Q0. Q is the 4-bit word. 4 bits are the output of these 4 D flip-flops, which are Q3, Q2, Q1, Q0. And this 4-bit word Q3, Q2, Q1, Q0 we write as Q. When clear goes to high, it will reset all the 4 D flip-flops and the word Q becomes 0, 0, 0, 0. When CLR returns low, the register is ready for action. When CLR goes high, output will be 0, 0, 0, 0. And when CLR goes to low, now the circuit is ready to work. Look here, we also added a control signal load also. Control signal load, and we have with this load goes to an inverter, that is NOT gate, which produces load bar. So control signal load with load bar. These are 2 lines. One line is for load and other is for load bar using this NOT gate. And we have 4 such combinations of AND OR gates. This is first AND OR gate, two AND gates, and output of which goes to OR gate. In the right AND gate, the inputs are load and X0. So when load is 1, this X0 will be transmitted from this AND gate, and when load is 0, this AND gate does nothing. Similarly, the left AND gate, inputs of the left AND gates are load bar and the output Q0 of this D flip-flop. So there are two AND gates. In the right AND gate, inputs are load and X0, and in the left AND gate, inputs are Q0 and load bar. When load is high, the right AND gate will be active and it will transmit this bit X0, and this X0 goes to input of D flip-flop, and this D0 becomes X0. And if load is low, then load bar is high, then left AND gate will be active because load bar is high. So the left AND gate will transmit this output bit Q0 to 0, and this D0 becomes equal to Q0. So this is the working of control signal load with load bar. When load is high, right AND gate will transmit this bit X0 and D0 becomes X0, and when positive clock edge arrives, this Q0 becomes D0, that is X0. And when load is low, then this right AND gate will be disabled, but then load bar will be high and left AND gate will transmit this bit Q0, and similar is for all these other D flip-flops. So when clear is high, output word Q equal to 0, 0, 0, 0. When CLR returns low, the resistor is ready for action. Load is a control input. It determines what the circuit does. When load is low, the X bits cannot reach the flip-flops. At the same time, the inverted signal load bar is high. This forces each flip-flop output to feed back to its data input. When each rising clock edge arrives, data is circulated or retained. So the register contents are unchanged when load is low. When load is low, load bar is high and left AND gates will then transmit this output Q0 to its input D0, and when positive clock edge arrives, Q0 then remains Q0 because D0 is also Q0, and similar for Q1, Q2 and Q3. So when load is low, data is retained. The word Q3, Q2, Q1, Q0 will remain the same. because all these 4 output bits goes to its input bit, and when positive clock edge arrives, Q0 becomes D0, Q1 becomes D1, Q2 becomes D2, Q3 becomes D3. And then Q0 is D0 and D0 is Q0, so Q0 bit is returned. Similarly, Q1 is returned, Q2 is returned, and Q3 is returned. Hence, this output word Q, that is Q3, Q2, Q1, Q0, will remains the same. This is for low load. And when load is high, then write and gets transmit these bits x0, here x1, here x2, and here x3. Then d0 becomes x0, d1 becomes x1, d2 becomes x2, and d3 becomes x3. And when positive clock edge arrives at all these 4 D flip-flops, the output Q0 now becomes S0, X0, Q1 becomes X1, Q2 becomes X2, Q3 becomes X3, and output word now becomes Q3, Q2, Q1, Q0, which will be now X3, X2, X1, X0. And it is for high load, when this load is high. So when load is low, the word will not change, and when load becomes high, this input word x3, x2, x1, x0 will be loaded in this register, and the word q3, q2, q1, q0 becomes x3, x2, x1, x0. Now if load returns to low, the foregoing word is stored indefinitely. This means that the x bits can change without affecting the stored word. Once this word is stored, x3, x2, x1, x0, and now if add load goes to low, then this word remains stored in it indefinitely, because when load goes to low, the output will not change. This is how this controlled buffer register works. Next is shift registers. A shift register moves the stored bit left or right. So there are 2 types of shift registers. One will shift the bits to the left, and other shifts the bits to right. Consider first this shift left register. Figure A is a shift left register. D in for input. D in sets up the right flip-flop. In these are, once again we have 4 D flip-flops with positive edge triggering. This is clock pulse. It goes all these 4 D flip-flops, and this triangle signal is for positive edge triggering. It will store the bit data input Q0 will be equal to D0 when positive clock edge arrives. When positive clock edge arrives, Q0 equals to D0, Q1 equals to D1, Q2 equals to D2, and Q3 equals to D3. Now here we add this D in. It is the input to the right D flip-flop, D0 is equal to D in. Let initially this Q is 0, 0, 0, 0. It means Q3 is 0, Q2 is 0, Q1 is 0, Q0 is 0. All these four output bits are 0. Now, when D in is 1 and Q is 0, 0, 0, 0, when D in is 1, then D0 will also becomes 1, and now Q0 will becomes equal to this D0, that is 1, when positive clock edge arrives. So when positive clock edge arrives, this Q0 becomes 1, and all these Q1, Q2, Q3 are 0, 0, 0. And now we have this word Q equal to 0, 0, 0, 1, because Q0 is now equal to D0 and D0 is D in and D in is 1. So when D in is 1, first positive clock edge arrives, which gives output Q as 0, 0, 0, 1. Now when Q0 is 1, now this Q0 goes to D1, the input of next D flip-flop. So D1 is now 1, and now Q1 will become equal to 1 when next positive clock edge arrives. So in the next positive clock edge, the output word Q now becomes 0, 0, 1, 1. And similarly, when next positive clock edge arrives, this word becomes 0, 1, 1, 1, and when next another positive clock edge arrives, this word Q becomes 1, 1, 1, 1. In this way, we see that when initially if Q3, Q2, Q1, Q0 all are 0, and now if we put D in as 1, then this 1 goes to D0 and first positive clock edge will produce as 0, 0, 0, 1 because Q0 becomes 1. And now this Q0 goes to D1 and Q1 will becomes equal to D1, that is 1, when next positive clock edge arrives. So for each next positive clock edge, this bit 1, which is D input, is 1. This bit will goes shifts to the left, and the word Q from 0, 0, 0, 0 to changes to 0, 0, 0, 1, and for next positive clock edge it changes to 0, 0, 1, 1. Then for next positive clock edge it changes to 0, 1, 1, 1, and then it changes to 1, 1, 1, 1. In this way, this bit 1 it shifts to left for each positive clock edge. Now we have this output word as 1, 1, 1, 1, and now suppose D input changes to 0, then successive clock pulses produce these resistor contents. This word 1, 1, 1, 1 changes to 1, 1, 1, 0 because D input is now 0. Next positive clock edge produce 1, 1, 0, 0, then 1, 0, 0, 0, then 0, 0, 0, 0. In this way, this 0 bit will shift towards the left. As long as D in is 0, subsequent clock pulses have no further effect. The timing diagram is shown in this figure B. This is the clock pulse, which is a square wave having fixed time period. For half of the time periods it remains 0, and for next half time period it remains 1. And these are the bits D0, Q0, D1, Q1, D2, Q2, D3, Q3. Initially D0 is 1. And Q0 is 0. Initially we have Q0, Q1, Q2, Q3 all are 0. Now when D0 become 1, then Q0 will become 1 when this positive clock edge arrives. It is shown by this dotted vertical line. Dotted vertical line shows that here this positive clock edge arrives, and at this positive clock edge Q0 will become equal to D0, that is 1. D0 is 1 here, because here now it becomes 0. So Q0, Q1, Q2, Q3 all are assumed initially 0, and D0 is 1. When first positive clock edge arrives, Q0 becomes 1. Now D1 is equal to Q0. So when Q0 becomes 1, D1 also become 1. See this diagram. Q0 is D1. D1 is equal to Q0 because output of this flip-flop is connected to the input of next flip-flop. D1 is equal to Q0. Similarly, D2 equal to Q1, D3 equal to Q2. So as soon as Q0 becomes 1, when first positive clock edge arrives, D1 then also becomes equal to 1. Now Q1 will becomes 1 when next positive clock edge arrives. This is the second dotted line which shows next positive clock edge. Here Q1 goes to 1 and then D2 also goes to 1. And when next positive clock edge arrives, it produces Q2 equal to 1, hence D3 equal to 1. And when next positive clock edge arrives, this Q3 becomes 1, and so on. And next it is shown when this D input becomes 0 from 1. In a similar manner we can explain this also. Next positive clock edge shifts the bits to the left. This is shift left. Now we see right shift. Figure C is a shift right register. Each Q output sets up the D inputs of the preceding flip-flop. In the right shift register, this Q3 is connected to D2. Output of each D flip-flop is connected to the input of preceding D flip-flop. Q3 is the output of this D flip-flop. It goes to the input of its preceding D flip-flop. Similarly, output of this D flip-flop, that is Q2, it goes to input of the preceding D flip-flop. And similarly, output of this D flip-flop, that is Q1, it goes to input of this D flip-flop, that is D0. So in the shift left register, output of a D flip-flop goes to the input of next D flip-flop, and so on. This is the shift left, and in the shift right we do this. Output of each D flip-flop goes to the input of preceding D flip-flop. Output of a D flip-flop goes to the input of the previous D flip-flop. Figure C is a shift right register. Each Q output sets up the D input of the preceding flip-flop. When the rising clock edge arrives, the stored bits moves one position to the right. When D in is 1 and Q is 0, 0, initially if we assume Q is 0, 0, 0 and D in is 1, then D in is here. Now in this leftmost D flip-flop, its input is D in. Initially if Q3, Q2, Q1, Q0 all are 0 and now D in is 1, then this D3 becomes 1, and then D3 is 1. Now Q3 will be equal to D3 for next positive clock edge. So Q3 will become 1 in the next positive clock edge, and this word 0, 0, 0, 0 now changes to 1, 0, 0, 0. Now Q3 is 1. This Q3 goes to input of this preceding D flip-flop. Now D2 is equal to Q3. So D2 is 1 and Q2 will becomes equal to D2 when next positive clock edge arrives. So at next positive clock edge, Q2 also becomes 1, and at next positive clock edge this Q1 will becomes 1, and at next positive clock edge this Q0 will also becomes 1. In this way, next rising clock edge will produces the words starting from 0, 0, 0, 0 to 1, 0, 0, 0, then 1, 1, 0, 0, then 1, 1, 1, 0, and then at last 1, 1, 1, 1. Controlled shift register. This is the circuit diagram of controlled shift register. There are 4 positive edge triggered D flip-flops. These are 4 D flip-flops. This is the clock pulse, and these are positive edge triggered D flip-flops. Clock signal goes to each of these 4 D flip-flops. This triangle symbol shows that it is positive edge triggered. Now this is the controlled shift register. This shifting action now can be controlled. To control this shifting action, these AND OR gates, there are 4 AND OR gates. Each consists 2 AND gate, and output of those 2 AND gates goes to input of OR gate. So this is AND OR gate. There are 4 AND OR gates connected to each of the D flip-flop, and This is control signal which we write as SHL. SHL is for shift left. This is used to shift left. One line is for SHL, shift left, and its upper line is for SHL bar. SHL bar is obtained by using a NOT gate. Now there are these two AND gates. Inputs of right AND gates are D in and SHL. When SHL control signal, shift left control signal is 0, then this right AND gate will be disabled. It will not work. And when SHL becomes 1, then it works and it will transmit this D input through OR gate to D0, and D0 becomes D in when SHL is 1. And next positive clock edge will produces Q0 equal to D0, that is equal to D in. And we see that this SHL bar goes to the input of left AND gate. For left AND gate, inputs are SHL bar and Q0, that is the output of this D flip-flop. So when SHL is 0, right AND gate is disabled, then SHL bar is 1 and left AND gate will then transmit Q0 to D0. So D0 will becomes equal to Q0 when SHL is 0, SHL bar is 1. So when SHL shift left control signal is 0, we see that D0 is equal to Q0. So similarly we have Q1, D1 is Q1, D2 is Q2, D3 is Q3. And for next positive clock edge, the word is retained. Q0 remains Q0, Q1 remains Q0, Q2 remains Q2, Q3 remains Q3. Q0 remains Q0 because D0 is also Q0 when SHL is 0. SHL bar is 1. So left AND gate will be enabled and it will transmit Q0 to D0. And Q0 is equal to D0 for next positive clock edge. So Q0 remains Q0. Similarly, Q1 remains Q1, Q3 remains Q3. So this word is retained. So word is retained, stored indefinitely until SHL is low. When SHL goes to high, then right AND gate will be enabled and it will transmit this D in to D0. Now D0 becomes D in and next positive clock edge Q0 will becomes D in. And for next positive clock edge, this Q1 becomes equal to D in and next positive clock edge Q2 will becomes D in and next positive clock edge will produce as Q3 equal to D in. In this way, this D in bit will be transmitted to left side. So this circuit will work as shift left resistor. Now there are two types of loading, serial loading and parallel loading. In serial loading, a word is stored in the shift register by entering 1 bit per clock pulse. To store a 4-bit word, we need 4 clock pulses. To store the word x equal to 1010 serially, put SHL high, make D in equal to 1 for the first clock pulse. If we want to store this word x equal to 1010, so first we will put D in equal to 1. 1 is the bit in this word in left side. So first put D in equal to 1, this bit of left side. So initially next positive clock edge will produce the word if we make D in is 1, then produced word will be 1000. Next we make D in as 0, then word will become 1000. Then make D in as 1 and the word becomes 1010, and in the last D in is 0. So in this order we make D in as for first clock pulse D in is 1, for second clock pulse D in is 0, for third clock pulse D in is 1, and for fourth clock pulse D in is 0. 1010, as this word is x equal to 1010. In this serial order, make D in initially first clock pulse 1, then 0, then 1, then 0. In this way, data is entered serially into the right end of the register and shifted left until all 4 bits have been stored. After the last bit is entered, SHL, which is control signal, is taken low to freeze the register. Next is parallel loading. In parallel loading, in serial loading, we are loading serially each bit. To store the 4 bits, we need 4 clock pulses. In parallel loading, we will load at the same instant in first clock edge. When first clock edge arrives, all 4 bits are loaded. For parallel loading, the circuit is this. These are the 4 bits x3, x2, x1, x0 which are to be loaded at the same instant. Now the change is that we now have these 3 AND gates in place of 2. And in the middle AND gate, the inputs are x0 and load. SHL control signal is here, and we now have another control signal, that is load, and we have load bar also and SHL bar also. Load and SHL, these two signal goes to NOR gate. And output of this NOR gate is connected to the input of left AND gate. Inputs of left AND gate are Q0, which is output of this D flip-flop, and output of this NOR gate which is having inputs as load and SHL. This middle AND gate is additional. Here the inputs are load and X0. When load goes to 1, this middle AND gate will be enabled and it will transmit X0. D0 becomes X0. And at the same instant, this D1 becomes equal to X1, D2 becomes X2, and D3 becomes X3. And when positive clock edge arrives, this output word Q3, Q2, Q1, Q0 will becomes X3, X2, X1, X0. All 4 bits are loaded at the same instant. It is when this load is 1. When load is low, and there is this control signal SHL also. SHL is high, then it will make the shift left action. So when SHL is 1, we keep load 0. And when we keep load 1, then we keep SHL as 0. So we can use this circuit for 2 purposes, for shift left also and to load this bits X3, X2, X1, X0 to this register. So if we want to shift left action, we put shift left SHL control signal as 1, then we have to put this load as 0. And if we want to load parallelly these all 4 bits, X bits, then we have to keep load 1, then we have to put this SHL as 0. In parallel loading, a word is stored by loading X bits directly into the flip-flops. It is shown in this figure. If load and SHL are low, output of the NOR gate is high. Load is low, SHL is low, output of this NOR gate will be high, and output of this NOR gate goes to the input of the left AND gate. Other input of it is Q0. So this Q0 will goes to D0. In this case, when load is 0, SHL is 0, left AND gate will be enabled because output of the NOR gate is 1. And output Q0 goes to D0, hence this Q0 is retained. So the word is retained when load is 0, SHL is 0 because left AND gate will be enabled and other AND gates are disabled. And if we want to shift left action, then we have to keep SHL as 1. When SHL is 1, load is 0, the circuit work as shift left register and this D in bit will be shifted to left for each positive edge arrives. And when SHL is 0, load is 1, this will load these bits X0, X1, X2, X0 at one instant at the next positive clock edge. So when load is low, SHL is high, the circuit acts like a shift left register. On the other hand, when load is high, SHL is low, the circuit acts like a buffer register because The X bits set up the flip-flops for parallel loading.